This question is about copper 2 sulfate and sodium thiosulfate. Part A. The enthalpy change of reaction for converting anhydrous copper 2 sulfate to hydrated copper 2 sulfate is difficult to measure directly by experiment. The enthalpy changes of solution of anhydrous and hydrated copper 2 sulfate can be measured by experiment. The reactions are shown below. In the equations, AQ represents an excess of water. Experiment 1. A student carries out an experiment to find the enthalpy change of solution of copper 2 sulfate for reaction 5.2. The student's method is that they're going to weigh a bottle containing copper 2 sulfate solids and weigh a polystyrene cup. Add about 50 centimeters cubed of water to the polystyrene cup and measure its temperature. Add the copper 2 sulfate solid, stir the mixture, and measure the final temperature. Weigh the empty bottle and weigh the polystyrene cup with the final solution. Experiment 2. The student carries out a second experiment with CuSO4.5H2O, reaction 5.3. The student uses the same method as in experiment 1. The student calculates the enthalpy change of solution of CuSO4.5H2O solid as plus 8.43 kilojoules per mole. Part 1. Calculate the enthalpy change of solution for copper sulfate solid, or copper 2 sulfate solid, for reaction 5.2, and determine the enthalpy change of reaction 5.1. Assume the specific heat capacity C of the solution is the same as for water. Show your working including an energy cycle linking the enthalpy changes. Firstly, we're going to be using the equation E equals mc delta T. So our m is our mass of solution. So that is the difference between these two. So that's 74.13 minus 23.43, and that equals 50.70. So we have 50.70 multiplied by, we're told that C is the specific heat capacity of water, because it's the same as water. So looking at our data sheet, that's 4.18. Then multiplied by the temperature change, which is the difference of these two. So that's 34.0 minus 20.5, and that equals 13.5 degrees Celsius. So multiplied by 13.5, that equals 2,861 joules. But we want kilojoules per mole because this is what we measure enthalpy change in. So that would be 2.861 kilojoules. Now we need to work out moles. So our moles is going to be the mass of copper 2 sulfate divided by its relative formula mass. So we're going to use the equation triangle of mass, moles, times relative formula mass. So the mass of copper 2 sulfate, that is going to be 28.04 minus 20.06, and that equals 7.98 grams. So 7.98 divided by its relative formula mass, which is 63.5 plus 32 plus 16 times 4. That equals 0.05 moles of CuSO4, or copper 2 sulfate. And then we do 2.861 divided by 0.05, and that gets us plus or minus 57.22 kilojoules per mole. But we're asked to work out the enthalpy change of solution and the enthalpy change of the reaction. So we've worked out the enthalpy change of solution, that's our minus 57.22 kilojoules per mole. To work out the enthalpy change of reaction, we need to minus our enthalpy change of solution of our hydrated copper 2 sulfate, which is 8.43 kilojoules per mole. So that's minus 57.22 minus 8.43. That equals minus 65.65 kilojoules per mole. And that is equal to our enthalpy change of reaction. To get the 6 marks for this question, you must correctly calculate the enthalpy change and the correct sign for the enthalpy change of solution of copper 2 sulfate solid, so minus 57.22 kilojoules per mole, and then correctly calculate the enthalpy change of reaction, so minus 65.65. This gets you the 6 marks for this question. Part 2. The thermometer had an uncertainty in each temperature reading of plus or minus 0.1 degrees Celsius. The student calculates a 20% uncertainty in the temperature change in experiment 2. Calculate the temperature change in experiment 2. So firstly, we need to look at the uncertainty of the temperature reading and the uncertainty in the temperature change. So when working out temperature change, you've used 2 temperature readings. So that means we're going to do 0.1 times 2. And then we're also going to multiply this by 100 divided by 20. That factors in our 20% uncertainty in the temperature change. So then that equals our temperature change of 1.0 degrees Celsius. So we write this on the answer line. To get the mark for this question, you must write 1.0 degrees Celsius, or just 1. Gets you the mark for this question. Part B. The standard enthalpy change of reaction and the standard free energy change for converting anhydrous sodium thiosulfate to hydrated sodium thiosulfate are shown below. Determine the standard entropy of anhydrous sodium thiosulfate and give your answer to 3 significant figures. So firstly, we're going to be using the equation delta G equals delta H minus T delta S. So using our delta H, our delta G values that we've been given, and T as 298 Kelvin, we can plug the numbers into the equation. So we get minus 16.1 equals minus 55.8 minus 298 times delta S. Rearrange, we get minus 298 delta S equals 39.7, and then dividing by minus 298, we get delta S is equal to minus 0.133, and this is measured in kilojoules per Kelvin per mole. Now we want to work out the standard entropy change for anhydrous sodium thiosulfate, and we've been given a hydrated sodium thiosulfate. So what we need to do is we need to do delta S equals, and we work out the entropy change for the hydrated sodium thiosulfate, so that's our reactants minus our products, so that would be 372.5 minus 5 times 69.9, and that equals 22.9 joules per Kelvin per mole. And then what we need to do is we need to do 22.9 minus 133. And how we've got 133 is we have converted our delta S to joules per Kelvin per mole, so that's 133 or minus 133 joules per Kelvin per mole. And that gives us 156 joules per Kelvin per mole, which we can then write on the answer line provided. To get the 4 marks for this question, you get a mark for using the Gibbs free energy equation. You get a mark for correctly working out delta S of minus 0.133 or minus 133 joules per Kelvin per mole. You get a mark for working out the delta S using the standard entropies given in the table, so 22.9 joules per Kelvin per mole. And then you get a mark for working out the standard entropy for anhydrous sodium thiosulfate, so 156 joules per Kelvin per mole. This gets you the 4 marks for this question. Part C. Sodium thiosulfate contains the thiosulfate ion S2O32-. The displayed formula of S2O32- can be shown as below. Part 1. Predict the OSS bond angle and name the shape of the thiosulfate ion. So what we're doing is we're looking at this bond angle for the sulfur in the middle. So what we do is we notice how many bonded pairs and how many lone pairs it has. Well, we have 4 bonded pairs and no lone pairs. So that means our shape is going to be tetrahedral. So you might be thinking, why is it 4 bonded pairs when we've got 2 double bonds? A double bond, a dative covalent bond, and a single bond, they all count as 1 bonding pair. So there's 4 bonding pairs here. And that means that our bond angle, if it's a tetrahedral shape, is 109.5 degrees. Writing 109.5 degrees and tetrahedral gets you the mark for this question. Part 2. In some of its reactions, the thiosulfate ion forms the tetrathionate ion, S4O6 2-. The S4O6 2- ion is a dimer of S2O3 2-. Draw the displayed formula for the S4O6 2- ion. There are 3 different combinations that will get you the mark for this question. So here I'm drawing the first one. And this is where the S- bonds to the other S- and the rest of the compound stays the same. So that's our first combination that would get you a mark for this question. Our second combination is where we have an O- and an S- bonding together, with the rest of the compound staying the same. This is another combination that would get you a mark for this question. And finally, we could have the S- remaining the same and both of our O- bonding together and forming an OO bond in the middle, with the rest of the compound remaining the same. This is our third combination that will get you a mark for this question. So either of these formulae would get you a mark for this question.